This video focuses on the fuse-to-fuse coordination and describes automated methods to analyze the coordination of all the fuse-to-fuse combinations in the feeder under no PB and with PB scenarios. In previous videos, we established the basic framework and the detailed modeling to derive the complete feeder model in OpenDSS from the GIS and other information by using MATLAB scripts. We also looked at the validation of this developed model by comparison of extensive time series analysis with feeder DAS measurements. So the next part, the one that we focus in this video, is to use this OpenDSS model commanded through MATLAB to run various fault cases and do the protection coordination analysis, specifically fuse-to-fuse coordination in this video. So we also introduced this very small feeder in order to better illustrate some of the concepts. So in this particular slide shows the protection zones in this simple feeder. So at the first level we have these sub-lateral fuses, which protects for all the faults in the respective sublaterals. We also have the transformer primary side fuses, which provide protection for transformer fault as well as faults on the secondary. So in all the you can see in both the sections of this feeder there are multiple sublateral fuses providing the primary protection. Okay, then we have the lateral level protection, which protects for all the faults in that complete lateral, and this needs to coordinate with the sublateral fuses to provide selectivity in the protection. The next level is the for all the faults downstream of the single recloser in this feeder. The recloser provides backup protection, and it needs to coordinate with the lateral fuses. Similarly, on the left side of the feeder, the substation relay also provides backup protection. It needs to coordinate with these lateral fuses. Okay. And the relay also provides backup protection for this segment of the feeder as well, and in this case it needs to coordinate with the main recloser. Also the settings and the coordination study methods will also differ based on whether the fuse clearing scheme or the fuse saving scheme is employed. So based on this discussion on the simple feeder, we can see that there are four main types of coordination that we need to study for the base case as well as different levels of PV penetration. The first one is the lateral fuse to the lateral fuse coordination. The second one is the recloser to the lateral fuse coordination. And here we need to worry about whether we use fuse saving or fuse clearing schemes. Then similarly on the left side of the feeder, we need to study the relay to lateral fuse coordination, and finally the relay to recloser coordination. So here is an illustration of a lateral fuse to lateral fuse coordination, and in this case for faults on this complete sublateral, we need to see how the fuse 1 and fuse 2 coordinate, and for that we need to look at the maximum fault case and the minimum fault case along this sublateral. And so for example, these are the TCC curves for the fuse 1, the main lateral fuse, and fuse 2, which is the sublateral fuse. And for a fault current, let's say 1000 amperes, clearly we can see that fuse 2, the sublateral, would clear first before the fuse 1 begins to operate. So that way the coordination is maintained. Now in the protection introduction video, we saw that when we consider the impacts of PV on the fuse-to-fuse coordination, there are two different cases that we need to study. The first one is when the PV is upstream of the two coordinated fuses, and in that case the fault current from the DG from this PV flows through both the fuses, and it increases the fuse current, increases the fault current seen by both the fuses. So looking at the TCC plots, the increased current from 100 amperes to, let's say, 120 amperes flows through both the fuses. So clearly fuse 2 still clears much earlier than fuse 1. Therefore coordination is maintained. So this is true for any PB upstream of fuse cases where fuse-to-fuse coordination will continue to be maintained. We just need to ensure that the increased fault current is well within the ratings of the two fuses. Case 2 is when the PV generator is downstream of the two coordinated fuses. So in this case, for a fault 1 as shown here, the current through fuse 1 and fuse 2 are still the same, and therefore the coordination would still be maintained. Fuse 2 would clear first, and we just need to ensure that the inverter actually senses an island and shuts off. But for a different fault, say fault 2 at this location, which is upstream of fuse 2, for this fault fuse 2 should not clear because the fault is not in this sublateral. But because of reverse fault current from the PV generator through the fuse 2 into the fault, there is a potential for the fuse 2 also to blow as a nuisance tripping or sympathetic tripping. And so this case needs to be studied for proper coordination, especially when the PV generator is a very large system and therefore provides a large fault current. Here is a flow chart of the automated method to study the fuse-to-fuse coordination in a given feeder. So starting from this detailed feeder network model, especially the adjacency matrix using MATLAB, we obtain all the possible fault cases relevant for this fuse coordination verification. So for a feeder of the size of Sandvik 4, we may have thousands of cases to run to study the fuse coordination along the entire feeder. I will use this simple example feeder that we've been considering to illustrate how we calculate, how we determine which all fault cases that need to be run for the fuse-to-fuse verification. So once the fault cases are determined, then MATLAB commands OpenDSS to run each of those fault cases, and OpenDSS gives the minimum and maximum fault current corresponding to each scenario for different PV penetration levels. And then for each of those fault runs, we compare the fault current with the fuse rating and make sure that there is no violation of the rating. Then for each of the fuse-to-fuse combination, we focus mostly on lateral fuse to lateral fuse combination. We calculate the time to operate for the obtained fault current using the fuse TCC curves as an equation. So we calculate the time to operate for the upstream and the downstream fuses, and based on the difference we can calculate whether coordination is maintained or how close they are to loss of coordination. And finally, these coordination, the cases which have loss of coordination are reported. So in order to compare the fault current obtained from OpenDSS for coordination verification, we need the time current curves of all the fuses and the recloses and other devices. OpenDSS does not yet have an extensive library of fuses and other devices with their TCC curves defined. So we obtain the definition of these time current curves for the different fuses and recloses using curve fitting of the either the experimental data from the data sheets or from the definition given in SIME-TCC. So there are 22 types of lateral fuses, some examples given here. For each of them, we used a linear interpolation method to obtain the TCC curves from SIME-TCC. So here is the smaller feeder example to illustrate how we determine the different fault cases to be studied for the fuse-to-fuse coordination. So in this small example, we only have 8 lateral fuses. So, and for each of these fuses, we need to run the maximum and minimum fault cases. So for example, considering the lateral fuse, fuse 1, which is right here. Okay. So for its coordination study, we need to The maximum fault case will be when we apply the fault at node 16 right after the lateral fuse. And we also need to study the fault cases corresponding to the minimum faults, and those would be at the end of like the node 21, node 20, and node 18, right at the primary of the transformers that are in this lateral. Similarly, you can also get the fault cases for each of the other 7 fuses as well. So as an example, for the coordination study between the lateral fuse 5, which is right here, and the lateral fuse 7, which is this sublateral fuse. For this coordination study, the maximum fault case is when the fault is right at the node 9, right after the lateral fuse 7. And the minimum fault cases would be at node 10, the transformer primary, then the other transformer node 12 and node 13. Okay, so we applied the developed methods on the complete Sandvik feeder for lateral fuse coordination study, and from the MATLAB we found that there are a total of 676 fault cases that needs to be applied, and the resulting fault currents and analysis with MATLAB revealed that there are 39 miscoordination cases, and this is even when the PV systems were not considered. So even under the no PV situation, there are 3 combinations between T40, K80, K50, K80 and K50, K65. We have a potential for miscoordination, and those are all those 39 cases are highlighted in this feeder diagram. And when we include the PV, it does not introduce any additional miscoordination. So here is an illustration of one of those miscoordination cases, specifically T40 to K80 coordination. So here is the that part of the feeder zoomed in. The fault is applied at this point. K80 is the downstream fuse that should operate, and T40 is the upstream lateral fuse. By looking at the TCC plots, we can see that for the corresponding fault current obtained from OpenDSS, the T40 operates earlier than K80, resulting in miscoordination. This one example of a PV downstream of coordinated fuses, and to study whether there is a miscoordination in this case. So we consider one of the 2 larger utility scale PV systems on the Sandvik feeder, the Cromer PV, and we consider a fault just upstream of the transformer. So for this fault should be only this lateral fuse that clears, and not the transformer load side fuse. But there is a potential for this to act if the fault current from the PV is large enough in the reverse direction to feed into this fault. Okay. But from the OpenDSS results, here are the current values. When the fault is at this location, the upstream transformer fuse sees a current of 1924, and it clears within 0.01 or 0.02 seconds. Whereas the downstream fuse, the load side fuse, only sees the fault contribution from the Cromer PV in the reverse direction though, and that value is 458. So that is 200% of its rated current, and at this voltage levels. This is, I think it's 480 volts 3-phase. The opening time, again calculated by MATLAB, for the given TCC curves is 0.9 seconds. That is well above the 0.02 seconds that under which the lateral fuse operates. Therefore, the load side fuse does not blow, maintaining coordination. So here is the list of all relevant MATLAB scripts that we have developed that we need to run to study the different protective device coordination. So in the remaining part of this video, I will just quickly go through the lateral fuse coordination, specifically run these 3 MATLAB scripts, and look at some of the interesting results. Okay, so let's run the MATLAB scripts corresponding to the fuse-to-fuse coordination study. So the file that we need to select is the protection coordination lateral fuse with PV. Okay, so let's very briefly look at the this particular script. So it starts with so getting all the network topology information Then it defines the TCC curves for all the lateral fuses. As you can see, it reads from the fuse TCC. Then the next several sections correspond to getting all the lateral fuses downstream of the recloser, downstream of the substation relay, then all the transformer primary nodes that are downstream of the lateral fuses, and so on. So basically determines all the fault cases to be run. Then all the faults are applied on the downstream transformer primary nodes for fuse transformer coordination, lateral fuse transformer fuse coordination study. Then after it runs the open DSS, all the lines and transformer currents are obtained. So that is used to calculate the upstream and downstream lateral fuse current, and using that and the TCC curve information, the fuse operating time for both upstream and downstream fuses are calculated, and finally the determination on how many, if any, have miscoordination, and those locations are reported. They are plotted on the feeder diagram. Okay, so let's run this script, and so it runs the fault cases for each of the fuses. Actually, for all the fuses which have at least one downstream fuse. So for example, J equals say 12, that corresponds to one particular fuse, and for that we need to run several fault cases corresponding to all its downstream fuses and the determined fault locations. So once it has run all the fault cases, like this J equals 129, this refers to faults for 129 fuses which have at least one downstream fuses, and I think the total number of fault cases that were run is 676. So once that is completed, we can look at the main results. So for example, this downstream fuse current magnitude has the current magnitude of all the downstream fuses for the fault cases studied, and the lateral fuse time has the corresponding fuse operating time again for each of the cases that were run. So it's still updating. Okay, so here are the fuse operating times for all the downstream fuses for the cases considered. Similarly, we can also get the upstream fuse current magnitudes and the operating time. Let's see, right here, the upstream fuse current magnitude and lateral fuse clearing time, and based on the difference between the fuse times for the upstream and the downstream fuses, we can determine coordination. And this entry, the fault STR fuse core, that has all the fault cases that are applied, all 674 cases. And the next entry, the with error, so that shows only the fault cases that resulted in some miscoordination. So these are the 41 fault cases that resulted in miscoordination with their corresponding node IDs and the phase in which the fault was applied. The script also gives the location of these miscoordination cases on the feeder diagram. So these are the 41 cases in red circles which had the miscoordination, and we can even zoom in on these regions to find out the exact location, so that we can look at changing the required changes in the setting. Finally, the procedure for running the fuse to recloser, the relay to fuse coordination is similar. And for example, to run the lateral fuse to the recloser with PV, we run this M file, and that gives us all the fault current magnitudes. And to compare for determining coordination, we need to run the recloser TCC fuse clearing for the fuse clearing strategy, or simply the recloser TCC phase for the fuse saving scenario. Similarly, when we run the lateral fuse to relay with or without PV, we need to run the relay TCC fuse clearing or relay TCC phase, depending on whether it is fuse clearing or fuse saving strategy.